How do we understand that? How do we figure out exactly that that's an equilibrium? We're going to take sort of a roundabout way and talk about something called game theory. Game theory is a tool that's often used to analyze oligopolistic markets, where we can help analyze a situation where firms behave strategically with each other. We look at the reactions that one firm has in the face of the other firm. Games have three important pieces. The first one is we have players. In this case here, we have the two firms. They also have strategies. What choices can they make? Can they choose the price they want to charge, or perhaps they can choose the quantity that they want to produce? Often you can think about choosing the size of your advertising budget or choosing the size of your manufacturing plant as being important decision variables. And then finally, we have outcomes. And the outcomes depend on what happens after all of the firms make their choice. What happens when each firm makes its decision? And what we can find is that my outcome doesn't depend just on the choice that I make, but it depends on all the choices of all of the other players in the game. We'll start with an interesting and illustrative example of our cartel problem, and this takes form of the prisoner's dilemma. And in the prisoner's dilemma, the way that it's formatted here, the police have caught two bank robbers, Bonnie and Clyde, but they can only imprison them for 1 year, and so they offer each of them the following deal. So each partner, Bonnie and Clyde, each get the following deal. If you confess and implicate your partner, you go free. So essentially, if you pin the rap on the other guy, we're going to let you go. If you don't confess, but your partner implicates you, you go to jail for 20 years. If you both confess, each gets 8 years. And if you both keep your mouths shut, you just get the 1 year sentence that they have enough evidence for. We can represent this game with a matrix, where we map Clyde's decision and Bonnie's decision and look at what happens given pairs of choices. Rather than looking at an individual strategy, you have to look at both. So we start with this. If Clyde confesses, he knows that Bonnie will get 8 years in jail if Bonnie also confesses. So we're thinking about what Bonnie might do. If Clyde confesses, Bonnie knows that if she confesses, she gets 8 years in jail. If she remains silent, she gets 20 years in jail. If Clyde remains silent, though, Bonnie gets to go free if she confesses, or goes away for a year if she remains silent. Now, these decisions are symmetrical from Clyde's perspective. Clyde knows if Bonnie confesses, he should confess and get 8 years versus remaining silent and getting 20 years. But if Bonnie remains silent, then Clyde's going to go free if he confesses, or get 1 year in jail if he remains silent. So in our game here, our players are Bonnie and Clyde. Our strategies for each of them are to confess and remain silent, and the outcomes are shown in the boxes. The outcomes depend on the pair of strategies that are chosen. So we're going to start by taking a look at Clyde's position first. And we note that if Bonnie confesses, Clyde should still confess, right? Clyde should confess if Bonnie confesses, because 8 years in jail is a lot better off than 20 years in jail. We're looking at the left-hand column. Right? Once Bonnie has chosen to confess, Clyde likes 8 years in jail better than he likes 20 years in jail, so he should confess. Now note that if Bonnie remains silent, we're still in a situation where Clyde should confess. Clyde is comparing no time in jail if he confesses versus 1 year in jail if he remains silent, conditional on Bonnie choosing to remain silent. So in either case, Clyde finds himself in a situation where he should confess. This is called a dominant strategy. Clyde has a dominant strategy when it is always in his best interest to confess. As it turns out, so does Bonnie. This game is symmetrical. They both have the same strategies and payoffs. And what we wind up with is what we call the Nash equilibrium. And the Nash equilibrium in this game is for both of them to confess. Now, notice something that's important. The Nash equilibrium for both of them to confess is not as good for either of them as it would have been if they both remained silent. But self-interest leads them both to confess. They both prefer to confess, conditional on the strategy that the other one has chosen, right? What we wind up with in a situation is, in the prisoner's dilemma, it's in each of their self-interests to do something that would be different than what they would have done if they were able to cooperate on remaining silent. Okay, now I want to describe what we mean by a Nash equilibrium. A Nash equilibrium occurs when each person is choosing its optimal strategy given the strategies chosen by the other players. That is, as long as everybody else is playing their given strategy, nobody wants to change their mind. We looked at the duopoly program before, and I want to demonstrate that the Nash equilibrium in this case is for each firm to produce 40 units. When each firm produces its 40 units, there are 80 units sold in the market, and the market price then is $30 according to the demand curve. In this case, what we want to show now is that neither firm has an incentive to cheat on the agreement. Suppose that one firm decided to increase its output and increased to Q equals 50. Then the honest firm produces 40, the cheater produces 50, so the total output is 90 units, and then the market price would be $25 each. And we can examine the profit of the cheating firm. 50 times 25 is $1,250 in revenues. Each unit costs $10 to produce, remember, so there's $500 in costs, which means the cheating firm's profits are $750. Notice that this is less than the $800 they would receive in profits if they stuck to the agreement. So in this case, we see that the cheating firm has no incentive to cheat. They should stick to the Nash equilibrium.